our test will be carried out in the same time and at the same link throughout all the students. We have about, I think, 8 sections, okay, which consists compared 160 student, okay. So it's quite a big, a large amount of student involved for this subject, for this course. So for this reason, we need to have a very um, smooth coordination and arrangement so that everyone can get a fair time, okay, sufficient for the for doing and submitting the test for the test one. I think you already aware, or you already know the link that that will guide you to the rehearsal today. I think one of the reason is we still need to do the online, because I think last time the some of lecturer asking about the availability of um, um, your preference, okay, whether you want to do the assessment test or exam online or face to face. So seems that everyone still prefer to do online, because I think only probably 2 or 3% is in the campus. Okay, but the rest is still in your hometown. Okay, so for this reason, most probably our test will be online, including of course test one is online, probably test two. Most probably the exam will be online. Okay, unless the arrangement has been changed by the school. Okay, so please get ready for this afternoon rehearsal at 5 p.m. Okay, so make sure you are ready. I think the rehearsal not take too long. Okay, as far as I understand, the rehearsal is only take probably 30 minutes. I noticed that some of you have quiz or other assessment on 6 o'clock. I'm not sure whether involve everyone or just only some of the student. But again, don't worry. I mean, the rehearsal only take about 30 minutes. If you the rehearsal probably take more time. Okay, you can leave the rehearsal as long as you know what you need to do during the test one, which is on this Saturday. Okay. Okay. So back to our topics. So we are in the transient heat conduction. I think from the yesterday class we have looked through the several equation related to the transient conduction, and I think today we try to do some exercise related to the transient conduction. I think at the end of this slide we have one example. Yes, this one. Okay. Okay. So this is the example, or not say example. This is exercise actually in your textbook. Okay. It's about cooling of that that has been burned in a kiln. Kiln is a furnace. Okay. Okay, with high temperature. So basically, this is a cooling process. Okay. And the cooling is the process where the temperature will be vary. Okay, except if you are in the chapter conduction, normally we assume that it is steady state. So the process will be steady state in one particular condition. So we try to calculate the heat transfer from that particular time. Okay, or at what specific time. But for the transient conduction, because the temperature is changing, so we will calculate the heat transfer within a specific duration. Okay, for example, in this problem, we need to calculate the time required. Okay, the time required, this one. Okay, the time required. Okay. So, like I say, this, the problem of the transient conduction normally related to the two types, whether you are dealing with a cooling process or whether you are dealing with heating process. I will try to find other example that probably related to the heating process. This is a cooling, okay? So how we know this is cooling? So you can read the problems. So a brick of 203 102. So basically this is a brick. So it's basically is in the rectangle type. So we have this brick. Okay. So this is a brick. So with the dimension 203, 102, 57, okay? So they say this is doesn't matter 203 millimeter times 102 times 57 millimeter in dimension is being burned in a kiln to 1000 degrees Celsius. So originally the brick is inside the kiln or furnace. Okay, so inside a kiln. Okay, usually you are aware of this. If the temperature of the surrounding is 1100 degrees Celsius. Okay, and then allow to cool in a room with ambient air temperature of 30 degrees Celsius. So this means this brick is bringing to the outside. Okay, after the brick have been burned or heated in this particular high temperature condition, so it is allowed to cool in a room. So this is a room. Okay, so with a condition of surrounding at 30 degree Celsius and convection heat transfer coefficient of 5 watt per meter squared. So the H value here is a 5 watt per meter squared. Kelvin. 5 watt per. Okay. So the brick has the properties. Okay. So the brick has properties of the density 1920, the specific heat 790, and thermal conductivity 0.9. So determine the time required to cool the brick to a temperature different of 5 degrees Celsius from the ambient air temperature. So what is this question asking? So if you want to ask anything, you can type in the chat box, okay? So that I know that you are with me solving the problem. You're not leaving me solving the problem alone. Okay, I hope you are there. Okay, to see the example how to solve this one. So the problem asking how long the time, how long required, how long the time required to cool down the brick to a temperature different of 5 degree from the ambient air temperature. So this means if originally the temperature of the brick is 110 degrees Celsius, so this means the initial temperature of the bricks, okay? So after it is go out, so the T initial of the brick, okay, is equal 1000 degrees Celsius, right? Because it is same like the furnace, okay? So you need to find what is the after, of course it will reduce the temperature, and the temperature now need to be reached at certain time, okay, for the brick to reach the difference, okay, between, so they say the T brick T surrounding equals to 5 degrees Celsius, okay. So meaning if the difference is 5 degrees Celsius, so you need to reach the brick temperature is about 35 degrees Celsius, considering the surrounding is 30 degrees Celsius. So we want to know how long the time required in order to change the temperature of the brick from 1100 degrees Celsius to 35 degrees Celsius. Okay, so you need to understand carefully the problem, okay, or the statement. Okay, sometimes when it is right 5 degrees Celsius doesn't mean that the final temperature of the brick is 5 degrees Celsius. So you need to know what is the 5 degrees Celsius is related to the different temperature or the temperature of the brick or the temperature of the surrounding. Okay. So okay, this is other problem. I need to find some space, blank space. Okay, so just now we have the brick, okay. So we have the brick. So originally T initial brick is at 1100 degree Celsius, and then you want to reach the temperature of the bricks, okay, after some time equals to 35 degree Celsius. Okay. Okay. So if you look back to your calculation, So the only equation that relate the transient conduction, okay, is using the lump capacitance method, okay, lump capacitance analysis. Okay, before that, okay, so this is the schematic. So you have to draw the actually the schematic is uh, quite easy, straightforward. I need to find the information from the textbook. So what's the dimension again? 203 here, 203, 57, and 102. Okay, so this is what dimension in millimeter. Okay, so the properties of the bricks. Okay, the properties of the bricks. So you have the density, how much? 1920. Sometimes the properties is not given, so you need to find the properties from the appendix. Okay, if you're not given, then you have to find from the appendix. So how to know which properties? You have to identify from the type of the material that you use. Okay, normally for the brick, you can just take the bricks properties as the building materials. Okay, so brick is considered the building materials. So you can take from there, from the table of building materials. So CP is 790 kilojoule per kilogram. Kilojoule per kilogram Kelvin. Okay, and the K value, thermal conductivity, is a 0.9 watt per meter Kelvin. Okay, so if I mark your assignment or your every number have their unit, okay, unless the number is dimensionless number. So if it is no unit, I will assume that it is meaningless. This means there is no meaning of the number that you are give. Okay, in engineering, other than dimensionless number count without unit is meaningless. So make sure you know that the unit, the number must come with unit. Okay, so this is your schematic. Okay, just a simple scheme, just a block with the dimension. And then you can say that it need to be cooling process. Okay, cooling process. Okay, so after the schematic, then you need to write down your assumption. Okay, so your assumption. I think the assumption you can check from the textbook if you're not sure. But what is the common assumption for transient conduction? How we get? Oh, sorry. How we get 35 degrees Celsius? Just realized someone asked me. Okay, 35 degree. Back to the problem. If you look to the statement, okay. Where is the okay? So read carefully. Determine the time required to cool the brick to a temperature different of 5 degrees. So you need to know the final temperature of the bricks should be have a different with 5 degree with the surrounding. Okay. Where is my my paper? Yes, this one. Okay. So how I can know this 135? T minus T surrounding will be 5 degrees Celsius. So this is the statement of the problem. The difference of the temperature at the final condition of the brick, okay? So delta T brick equals to 5 degree, which is the difference between the final temperature of the brick minus T surrounding is 5 degrees Celsius. So from here, so you know that T, you want to find the T bricks, and you know the surrounding is 30 degrees Celsius. So this is 5 degrees Celsius. So you know that the final temperature of the brick is 35 degrees Celsius. Okay. Do we need to put H also need in the properties? This is properties of the bricks. Okay. So you can the H is a properties. It's not a properties actually. H is a condition of the air. Okay. So if you want to put, you may put in the different area, different section, okay, or different compartment. Let's say this is the air. So the air have the condition of T surrounding about 30 degrees Celsius, and H equals to how much? 5, is it? Yes, 5. 5 watt per. Okay. H is H is not a properties. H is a convection coefficient of the air at that particular time. Right? Remember that H can be changed. H can be changed due to the velocity, due to the temperature, due to the geometry, due to the several other factors. Okay, and for our condition, the H is assumed to be 5. Okay. Okay, next one, the assumption. What is the common assumption under the transient conduction? Okay, so you cannot write a steady state anymore. Okay, this is not a steady state. If you write steady state, I will minus your works. No more steady state. Steady state only for the other problem, but not in transient conduction. Okay. So one of the assumption that you can use here is the properties of the bricks is constant. Okay, the properties of the brick is constant. Okay, so this is so that you can use the properties as it is throughout the analysis. Okay, because sometimes I'm not sure whether you still remember or not. If the properties have a different homogeneity, then you may have a different value of density, different value of Cp, different value of K. Okay? Same goes with the temperature. Okay, properties of the brick is keep constant. At the given so let me mention the properties. It's keep constant, and because we know that the temperature is changing from 1000 degrees Celsius to 35 degrees Celsius. Okay, But if you look these properties, okay, just to check, okay, these properties I believe taking from the appendix. Okay, let's say whether we can find the properties of the brick so that you can know how this value is come from. Okay, bricks, building material. Oh, this is in imperial unit. You need to open the table in the SI unit. Building materials. This one, solid brick. This one, okay. Okay. Can you see? This is the brick. Okay. Or they give the value of density 1922. It is written 192. It's quite close. K is 0.2, and then here in the table, in the problem is giving you 0.9. Okay, so if you look the value for the bricks 1922, and the K is 0.72. Okay, the K. Specific heat is not given. Oh, sorry, this is oh, I think they're taking the not this. I think this is fire clay. Okay, not this one, because probably this the CP is not given, so we take this one. So we take this brick from the fire clay. Oh no, this one. Okay, there is another type which the specific heat is applicable. Okay. You know why there is several types? Because of the properties, and because of the density is different. Okay. So probably they should have the specific heat, but during the collection of this data, the specific heat for this particular brick is not available. So the only available here is 0.79, where the K value is 0.9 and the density is 1920. Okay, so this is the density, this is the K value, this is the specific heat. I think it's same like in the problems. Okay, but if you look carefully, these properties is take the value of at a mean temperature 24 degrees Celsius. So meaning that the properties is defined at 24 degrees Celsius. Okay. So if you look, so this is where defined at 24 degrees Celsius. But in reality, okay, if you finish this one, it's this analysis is subject to the minor error because the temperature of your properties is not within the range of the bricks. Okay, you can see here the bricks have a temperature at the 1100 degrees Celsius to the 25 degrees Celsius. Okay, so it's a bit, I mean, it's far from the properties of the bricks temperature definition. Okay, but still, this is part of the assumption. So that's why it is under your assumption. Otherwise, if you not put this, this mean you somewhat accurate. Okay, because this is just to put assumption, because the assumption used to simplify your analysis. Otherwise, you need to find the properties at the average temperature between the initial temperature to the final temperature. Okay. Okay. What are the assumptions? If you look to the textbook, I think other suitable assumption like negligible radiation. Okay, so they should be have radiation effect, but we don't really consider the radiation. Okay, so negligible or neglect the uh, the heat by radiation. Okay, and I think this is, there's no steady state. Okay, this is a 1, this is a 2, this is a 3. Okay, I think the number 3, what you can say that the temperature, the initial, because the problem is not say that the temperature of the brick is 1000 degrees Celsius, but they only say that the 1000 degrees Celsius. So we can say that initial temperature of the brick is same as temperature inside the kiln. Okay, or the temperature inside the furnace, which is at 1000 degree Celsius. Okay. One-dimensional analysis. Yes. Also, we can say this is a one-dimensional analysis for the okay. So one-dimensional analysis of heat transfer. Okay. How to know whether the question asks for brick for fire clay if the properties not given? You can say it in the problem. Actually, if you taking a wrong materials, probably not say wrong material, taking different type of bricks doesn't matter. Okay, as long as the properties that the information of the properties is provided in the table. Okay, you may ask why I didn't take the common brick. Why I didn't take the brick face? I need the specific heat. Sorry, I need the specific heat value CP, because there is no other information here in the specific heat except this brick fire clay. Okay. Okay. For example, if let's say you want to take this plywood. Okay, this plywood is just because of a difference in the thickness. Okay. But if there is a different layer, just take the properties that you think that all the information that you are required is available. For example, I need a CP value, so that's why I took this number. How much? This three type. This three type. In fact, in this in the third one, there is two. There is three type. 1, 2, and 3 at the different density. Okay, so you know that material the brick have different density. You know why? Because of the quality, the cost. Some people like to buy a cheap bricks. Okay, so this cheap brick normally has higher bricks have a high cost of brick. Okay, normally related to the high dense bricks because of the materials to form this brick is completely solid. Okay, unless compared to the less dense, because of it is involve a lot of air during the preparation of the bricks. Okay, okay, so that is our assumption. Okay, next for the assumption, you can write down the properties of the form that you want to analyze. So in this case, is your brick that you need to analyze. Okay, the properties. I think you can write back the properties of the bricks. Okay, so the properties of the brick you can write here. Brick properties defined at 24 degrees Celsius. Okay, so you can write down here the properties of the bricks. Okay, next one is the analysis. Okay, so like I say, in yesterday class, so before we start the transient conduction, the first step or the first part to analyze is calculating the Biot number. Okay, because you want to know how far your calculation of the transient conduction using lump capacitance is far from the accuracy. Okay, or whether it is applicable or not. Okay, so first you need to calculate the Biot number. So Biot number, what is the equation? So the Biot number equals to H L C divided by K. Okay, where H is the convection coefficient of the air because of this where the convection occur. Okay, so if you look, if I can draw the bricks. Okay, so during the cooling in the room, so heat will move. Okay, originally the heat, the cooling. So the cooling is from the system to the outside. So basically, so heat is moved from the heat to the outside. Okay, so basically you have heat move by the conduction and heat move by the convection to the outside. Okay, so imagine that this is the center of the system. Okay, so H here is the H of the air during the convection, and K here is the K of the brick for the conduction, because we want to know the ratio of convection and conduction resistance. So what is the LC here? LC is your characteristic length. C is a characteristic length of the brick. Okay, where you can find using V divided by A. Okay, volumes of the bricks divided by the surface area. Okay, So how to find the characteristic length? So the volume, how many assumptions required for every equation? Normally at least 3. Okay, at least 3. For me, if you ask me, at least 3. But some problem probably required 2. But in my case, try to make it habit is at least 3. You can have more assumption, okay, because sometimes the assumption can use to support your analysis. Okay, so make it a habit. Try to put assumption as many as at least 3 assumption. You can put it more, but at least 3. So the volume, so I think it's a bit long. So what is the dimension just now? 203, 102, 57. Okay, so 203, 52, 107. Okay, millimeter. Okay, so if I can calculate here the volume, well, you can put in millimeter first if you want, or you can change to meter. Let's say you just use the value 107 plus 203. So this is the volume divided by the surface area. Okay, so you have how many surface area? 6 surface area. Okay, so 2 times 5, 2 times 107 plus 2 times what? Sorry, 4, right? 4. They got 6 surface exposed to the convection. Okay, assuming that the bottom surface also have convection. Four times 203 times 52. Oh, wait a minute, not 4, I think 2. Also 2. Plus 2, 203, 107. Okay, so you got 3 different surface area. Okay, you can you calculate so that you can get the answer? So this is chapter 4.
Sir,
Yes.
kalau daripada soalan tu length tu 102 bukan 107.
Saya silap 102.
57.
102, yes, okay, sorry. 10257, okay, thank you. Sorry guys, 57, this is 102. Okay, so this is 57. Um, Five seven 102. This is 57 102. Sorry guys, if you give me answer, probably you need to calculate unless you use the right dimension. 14.92411. Wow, there is many. 15.49. I think the last one is the correct one. Okay, 15.492 millimeter. Okay. Okay, thank you. So that is in millimeter. So from there you can calculate the Biot number. So therefore the Biot number equals to HLC divided by K, and H is a 5 watt per meter squared Kelvin. LC is a okay, this one you need to change in a meter. 15.492 times 10 to the power of -3 divided by K. What is K value? 0.9. How much? The 0.08 0.0861. Okay, so this is Biot number, no unit. Okay, so what is the meaning of this value? So the Biot number value is smaller than 0.1. Okay, so since the this is C, since the Biot number is smaller than 0.1, okay, so the use of lump capacitance analysis is suitable, okay, or applicable for this problem. Okay. If let's say you got the value let's say you got the value probably 0.5, okay, or probably 0.2, which is greater than 0.1. So you can say the use of lump capacitance analysis is approximate, okay, it's approximate because it is a bit larger than 0.1, but still can be acceptable. Okay, or you can say the use of lump capacitance analysis is not suitable. However, for the analysis, for the lump capacitance analysis, the use is to the lump system analysis can be used as a estimation. Okay, it can be estimation or can be approximate. Okay, to the actual condition of the problem. Okay, that you want to solve. Okay, or probably let's say at what condition that you cannot use. I think it is greater than 1. So if your Biot number greater than 1, so the use of lump capacitance is no longer valid. Okay, so the use of lump capacitance analysis, LCA or LCM, lump capacitance method, is not valid. Okay, so if not valid, what you want to do? So you have to use the second method, which is a special effect. So how to do the special effect? Then you need to read the second part of the chapter 4, which is I'm not covered, but probably required when you are working as you are become R&D engineer, for example. Okay, so do not say that I'm not teach you how to solve this. You can solve, but you need to get further reading on how to solve the Biot how to solve a transient conduction. Okay, if you get the Biot number greater than 1. Okay, if you go to the textbook. Okay, what is the chapter 4? Okay, this chapter 4. So if you look 4.2, yeah, this one. Okay, so this is suitable when you have dealing with a greater Biot number, or you want to be more accurate. Okay, because if you see in these topics, you learn about a bit long equation where you need to have use this table. Okay, I think this is a Bessel function. Okay, with a different Biot number. See here, this table. In fact, you can use this method if you have a low Biot number, but this Biot number is more applicable when you have a larger Biot number. Okay, so look here, it is suitable if you have a larger Biot number. But for the smaller Biot number, less than 0.1, you can use a special effect. But if you want to get more accurate, probably your boss require, I want the more accurate analysis, then go to this method, special effect. Okay, I'm not teach you, so you have to read this in much more detail. Okay, this one, special effect. Okay, where's the okay, next one, we need to do the analysis number 3. Okay, analysis of so analysis of transient conduction. Using lump capacitance analysis. Okay, so using lump capacitance analysis, the temperature variation, okay, the temperature variation of the okay, of the bricks. Okay, so you can get T the temperature at the specific time minus the T surrounding divided by T initial minus T surrounding equals to exponential of time constant and multiply by t, time. Okay? So you know that you have the info from this data. You got this value. Okay? You got this value. What is the value? Here the value is 35 degrees Celsius. You have the surrounding temperature 30. You have the initial temperature which is at 1000 degrees Celsius. And you have the temperature of the surrounding 30. Okay? You need to find the B and you need to find the time. Okay? So the B you can calculate from the terms of lump capacitance. Okay, so what is the B? So the B can be found from the equation 4.5, okay, where B equals to HAS divided by rho density, the volume time the CP, specific heat. Okay, so you need to, okay, I think every value is given. So the H value 5 times the surface area of the brick, I think you already calculate this, but this time you need to calculate in meter. Okay, so if you already calculate in millimeter, you have to convert in meter. Okay, the density, what is the density? The density is 1920. Okay, the volumes, I think this is the volume of the bricks. Again, you already calculate and make sure you change this in, you change it into meter cube. Okay. Specific heat. The specific heat is 790. How much? If you can calculate this. Oh, in fact, you don't need to calculate. In fact, you already calculate LC, right? Yes. Sorry. The same equation actually, if you already calculate, you can relate with the LC. H divided by rho CP LC. Okay? Because V over A is a LC. The one that you just calculate just now. So 5 divided by 1920 times 790 times how much? The value 15.492. 15.492 times 10 to the power of -3. 2.1278. 2.1278 times 10 to the power of -4. Okay, so what is the unit? S -1. So it's a reciprocal of time. Okay, so you can put back to the equation. So you put back to this equation. So 35 minus 30 divided by 1100 minus 30 equals to exponential negative 2.1278 times 10 to the power of -4 t. Okay. How to solve this? You can use the LON, basic law. So basically you can calculate, actually if you can change this into a basic LON form, okay? So how this one become down here. So T equals to this is 1 over B, 1 over B. 2.1278 times 10 to the power of -4 ln. Okay, it's 35 minus 30 divided by 1100 minus 30. Okay, because from exponential you bring the exponential to the left, you will get a basic log. So someone can get T. How much? Oh, sorry, negative. Yep. Negative, because we got negative here. This one. So how much the T? Oh, 25. What? 25. Can you change to hour? 25,218.42 seconds. Can you change to hour or minute? In minute, or I think hour. 1 hour go to 3,600. So I think it changed to how long in hour. So divide by 3,600. Exactly? Oh, 7. 7, okay, 7.005. Okay, so it is close to 7 hours. Okay, 7 hours. So, meaning, in order to reach the temperature from 1100 degrees Celsius, okay, a brick's temperature from 1100 to 35 degrees Celsius, you require 7 hours. Okay, 7 hours of the time. Okay, understand? Okay, so you require 7 hours for one bricks to cool down from the high temperature of the furnace kiln to the room temperature within 5 degrees Celsius. Okay, so this means before you want to ship or sell the brick, you need 7 hour cooling period. Okay, so this require further analysis if you want to produce how many bricks in order to sell to the client, to your customer. Okay, because this is a kind of a process, because when you go outside, when you go industry, time is very important for them. Time is very important. Time is money. Okay, so of course we need to have a very short process, but greater income. Okay, so if your boss require to calculate how long this brick can cool down before sell to the customer, then we say it is required 7 hours. Okay. Actually, this equation, this concept of analysis is using by the forensic. You remember how forensic know that, okay, this body already died 3 days ago. This system already been, this system already been burned for how long? So they use the same analysis. They use the lump capacitance method. Okay, so they know how long, what is the initial temperature, what is the final temperature of the body. Okay, so how long the process will be took by calculating this time. So probably you are one of the forensic, you can estimate how long that this the body already did after some hours, based on the temperature of the normal temperature of the body compared to the temperature of the body during the measurement. Okay. Okay, so that is the beauty of this method. You can apply in any kind of situation where the cooling process is taking place. Okay. Any question? So if this is the cooling process, I think there is one example of, I think this example, this is another example. Let me read. This one is suspension system. If you have any question, you can ask in the chat box. Okay. So this is another example of the transient conduction, but in the heating process. Okay. So if you look to this example, yes. Okay. This spring in suspension system of automobiles are made of steel rods heated and wound into coil while ductile. That means they want to say that the process of fabricating the spring in the suspension system is during the steel is still hot, okay, into coil. So they give you the information of the steel, okay, all the density, specification, and the K. The diameter and the length is to calculate the volume and the area. Okay. The steel rod are heated in an oven with a uniform convection heat transfer coefficient of 20 watt per meter squared Kelvin. The steel rods were heated from an initial temperature of 2 to desired temperature of 450 degrees Celsius. Okay, before being wound into coils. Determine the ambient temperature in the oven. If the steel rods were to be heated to the desired temperature within 10 minutes. Okay, this problem, okay, how can I draw this? So if I can, okay, I hope you can see the problem just next to the my blank sheet. Okay, so okay. Do you understand the problem? I think I will not finish this one, but I give you some idea how to solve this. In fact, this is problem from the textbook, I think. Yeah. Problem 4.22. 4.22. Let me check here. Do you have this kind of example? Four point two two, is it correct? 4 point. No. Where? Yeah, this one 4.25. Okay. So this problem, is quite difficult. Where is the? Okay, this one 4.25. Okay, I just circle the problem. This one. Okay, this problem, okay, is a heating process. Okay, so this is a heating process. Okay, differ from the initial exercise that we do just now is a cooling process. This time is a heating process. Okay, so what this the problem is all about. So originally you have a steel rod. Okay, so this steel rod, okay, can put it. Okay, this steel rod need to be heated. Okay, going into the furnace. You say furnace, oven. Okay, so this is a oven. Okay, and then within this high temperature, so they will turn the rod into coil. Not very good my drawing. Forgive, my drawing is very bad. Okay, so before it is transformed into the assembly as a suspension system. But of course, this process, the forming, okay, the formation of the steel rod from the rod into the coil need to be at a high temperature. Okay, at which it is say that it is at 450 degree Celsius. Okay, where the original temperature of the rod is a 20 degree Celsius. Okay, So here your Ti of the initial temperature of the rod is 20 degrees Celsius, and your T final, okay, or you don't know the time, the T time will be at 450 degrees Celsius. They give you the time, okay? Because you you read here, the steel rod are heated in an oven with a 20, and the steel rod were heated from initial temperature 20 to 450 before being worn into coil. Determine the ambient temperature if in the oven if the steel rod were to be heated to the desired temperature within 10 minutes. So this means this T equals to 10 minutes equals to 450 degrees Celsius. Okay, within 10 minutes, the temperature of the rod, okay, need to be increased from 20 to 450 degrees Celsius. Okay, so meaning here, what the T time minus T surrounding divided by T what this one is T I minus T surrounding, okay, equals to E negative BT. Okay, so you need to so the temperature of the final is 450. So the time is given is for 10 minutes. So you need to change the time is into second. Okay. So how long you need to reach the temperature? Is it 450 as well? So this is a 450. Ti is a 20. So this is 450 degrees Celsius. So okay. First, you understand the problem. So you can find. So you need to find the temperature of the oven. Oh, so you need to find the temperature of the oven. So this means you need to know if the final temperature of 450 degrees Celsius. So the only information that not available here is the ambient temperature in the oven. So this one, okay, T in here. That should be a bit higher than the. So you need to find this. Change this color. So you need to find this value. Okay. So the initial temperature is 20 degrees Celsius. The temperature of the final of the system should be 450. The time required, okay, so you need to change this into second from 10 minutes. And the B, the time constant value, the B value can be calculated using the information given. Okay. So finally, you need to find this information, the surrounding of the furnace or of the oven. Okay. So like the example just now, you need to find draw the schematic and then state the assumption. Okay, I think the properties is given, so you can use the properties as it is, as given in the problems. So next one, you need to calculate the Biot number. Okay, so let's say you draw the schematic. Sorry, you draw the schematics. Assuming that you can draw the schematics, you can find the assumption. Okay, and then you write down the properties of the rod, steel rod. Okay, and then you start the analysis. So you start with the Biot number calculation. Okay, so what is the Biot number? Is actually can be get HLC divided by K. So you have to remember that this is rod. Okay, so with the diameter of how much? 2.5 centimeter, and the length equals to 1.27 meter. So from here you can calculate by the surface area. Okay. So from there you can calculate the Biot number. HLC divided by K. So you can get this. H is given 20 watt, and K is a what? 63.9. Okay. And then you can know whether what is the value Biot number, and you can check whether your calculation is accurate, suitable, applicable, or is it approximate, or it is not valid. Okay. Normally it should be within, from my experience doing some problem with textbook, whether it is accurate, applicable, or approximate. Okay. So next one, you do the lump capacitance method analysis using the equation T final Tt minus T surrounding divided by Ti minus T surrounding equals to exponential negative Bt. So you know the times. So you know the times, which is 10 minutes. So equals to 10 times 60 seconds. So which is this is a 600 second. Okay, and then you need to find the B, which is what is the B? B is what is just now B? H divided by rho CP LC. Okay, and you should get this B. So you have so you get everything except one unknown. So you can find the T surrounding of the oven. Okay. Oh, finish this. So once you get the temperature, so you can say here that the temperature of ambient for the oven is what? To heat the coil or rod at temperature of 450 degrees Celsius. 450 degree Celsius. Okay, it's just a discussion. Sometime in the problem you just reword your analysis in the word form, but sometime they ask you opinion. Okay, for example, I found there is some example related to the comments. Okay, this one, for example. Okay, if you look here, this 4.29 problems. Okay, first they ask you to how long it will take to warm up the milk from 3 degree to 38 degrees. Okay, and then once you calculate, this question asks you some theoretical question. Can the milk in this case be treated as a lump system? Why? Okay, I think this you already calculate the Biot number, so you need to answer this by comparing the Biot number value that you got with the suitable Biot number that applicable for the lump capacitance analysis or lump system analysis. Okay, this normally required. This is example of how our test or our final exam looks like. Okay, so they ask you to do some analysis, and then at the end of the question they ask you the descriptive or the understanding question related to what you have done in the analysis. Okay, any question? Okay, any question, guys? So if not, I think that is for today. So try to do any other additional exercise. I think you can do from 1 until what? How many equation available? Until 442. There is 42 question available related to the lump capacitance analysis. Okay. In fact, there is some understanding. I try to next class. I will try to ask you some understanding question. Okay, after we finish discuss in the lecture, after the lecture slide is finished, so that I can know whether you really understand or not. Okay, so if this is the face-to-face class, I can pick one of you, then assist me to understand, to give some explanation on the descriptive question related to the topics. But in here, call your name, but I'm not sure whether you are available or not. Okay, sometime I'm calling but no answer. Okay, any tips, reminder before test one? You must have the textbook. Okay, you must have this textbook. This is the tips. Okay, if you don't have the tip,